Okay, talking a little bit about electric charges, fields, forces, potential energy. I have acquired a little bit of a cold since I last did one of these, so apologies if I sound a bit odd. I'll try and keep that as under control as I can. So I just made the point here that we mostly talk about microcoulombs or that kind of order rather than full coulombs. The Coulomb constant, 9 by 10 to the 9, means that if you have two 1 Coulomb charges a metre apart, there are 9 billion newtons of force between them, which is vast. So we tend to have much smaller charges than a whole Coulomb. So in this case we've got an object, it's just a metal sphere, and it has a charge of plus 200 microcoulomb on it. And 200 by 10 to the minus 6 is 2 by 10 to the minus 4 Coulomb. So we're working Coulomb. And we're going to measure out. We're interested in a point 2 meters away to the west and finding out what's happening at that point due to this particular charge. So first question, what's the electric field 2 meters away from the charged object? So we've got the equation E equals K, Q, where there's just the one charge, we'll use a capital Q, over R squared, equals 9 by 10 to the 9 times 2 by 10 to the minus 4 over 2 squared equals 4.5 by 10 to the 5 newtons per coulomb. So even at these microcoulomb scales, it's still on the order of hundreds of thousands of newtons per coulomb, 10 to the 5. So we can also work out the electric potential at that point. So not the potential energy, but the potential, which is kind of generalized. So part 2, V equals, and it's actually very similar, KQ, but over R rather than R squared. So the top line of the equation is just the same, 9 by 10 to the 9 times 2 by 10 to the minus 4, but the bottom line is R instead of R squared, so it's just 2. So that means overall, if we do the maths, 9.0 by 10 to the 5 volts. The unit of electric potential is the volt. A volt is a joule per coulomb. So instead of a force of newtons per coulomb, it's a number of joules per coulomb. In other words, it takes a certain amount of energy to get a coulomb of charge to that point. So then we're asked, what's the magnitude and direction of the force if we place a minus 15 microcoulomb charged object, minus 15 microcoulomb, 2 meters to the west of the charged object. So we've done that. This is the point we've been looking at. What's the magnitude and direction of the force on it? Okay, it turns out there are a couple of ways to do this, the easy way and the slightly less easy way. They're both pretty easy, but the first method is we have an equation F equals QE. The force is equal to the charge times the electric field at that point. And in question 1, we already calculated the electric field at that point to be 4.5 by 10 to the 5 newtons per coulomb. So minus 15, we can use the minus. It just tells us that it's an attractive force rather than a repulsive force. If the charges were the same, they would repel one another, but they're opposite, so they'll attract. So the force will be in the direction to the east, toward the other particle rather than away. So what did we say? Minus 15 microcoulomb is 1.5 by 10 to the minus 5 coulomb times 4.5 by 10 to the 5 Newton per coulomb equals 6.75 Newton. So the actual force on the particle is 6.75 Newton. So that's one way of doing it. The other way of doing it is using our different equation, which is F equals K Q1 Q2 over R squared. Now, if you actually look at what you're doing there, you're basically taking the F equals QE, but that E, if you go further up the top, is just KQ over R squared. So you've basically just done the same thing either way. You've either substituted in the E or not. Let's give ourselves enough room because that's going to get a little long. Equals 9 by 10 to the 9 times charge number 1 is 2 by 10 to the minus 4. Charge number 2 is minus 1.5 by 10 to the minus 5 over 2 squared is going to end up giving us a force of, unsurprisingly, 6.75 Newton, the same as by the other method, which you would hope would be the case. Okay, and then we should go back and find out what question 4 is. Calculate the electric potential energy of the minus 15 microcoulomb charged object at this position. So the electric potential energy is going to be, actually let's go over here, give ourselves some space, for U equals K Q1 Q2 over R rather than R squared. So when we're dealing with forces, we're using R squared, falls away as the R squared. When we're using energy, falls away as R. So equals 9 by 10 to the 9 times 2 by 10 to the minus 4. Oops, that's an error. 2 by 10 to the minus 4 minus 1.5 by 10 to the minus 5 over 2, and that's going to equal 13 joule. Minus 13 joule, because remember we had a minus sign in there that wasn't cancelled by anything. That means that by bringing this closer, we are not doing work on it, we are having work done by it because it's trying to get closer. Does that make sense? If we had two oppositely charged particles at distance infinity from one another and we bring them closer together, that's what they're trying to achieve. So we actually we can gain energy from that, take energy out of the system rather than add energy to the system. If we had two opposite charges that were repelling each other and we had to bring them closer together, we would have to put work in, we would have to do work to bring them closer together. But in this case, they want to be closer together, to anthropomorphize a little bit, and so we could get work out if we were to bring it closer together like this. Okay, that's the end of those ones.